Welcome to the fourth lecture. We do have a long way to go. Five lectures per week, 8 weeks, 40 lectures. You are on the fourth, 36 more. Wow! I think that's quite intimidating. But you know, to learn something, you need to be patient and you need to go on for a while, and gradually you will get a hang of things of what's going on. Because what I present to you is very organized knowledge, but I would also like to tell you beforehand that no knowledge that you see in presented to you in such an organized manner has ever been developed in an organized way. It comes in bits and pieces done by various people in various times, found in many years after the death of the person who did it. The true discoverer is often forgotten and somebody else takes the name. So, it is filled, these stories of such things are filled in science. So, but finally a good amount of knowledge which is really useful, really applicable, really needed by humanity has been organized into and taught to people, so that they can also use them in their profession, in their activity and whatever they want to do. So, as a result, when you learn organized knowledge, you really need to be patient. You need to be patient, need to sit down and listen as to what the hell is going on, and then only you will gradually have a little understanding of what you are doing. So, I would try to be more different time. I try to be more conversational with you and try to be more give you more motivation than anything else, in the sense that I would like to talk to you, and though I know nobody is sitting right here in front of me, but I know there is a huge gamut of people who would be finally observing this, and in keeping in mind that imaginary audience, I would keep on doing these conversations with you. Now, what I am going to learn today is matrices and determinants, and this is something you must have already heard in your high school. So, it is lecture 4. I have already written in that electronics lab also, matrices and determinants. Now, this you might suddenly think, why I am getting out of this idea of vectors, functions suddenly into such strange terms, matrices and determinants, and those who know a little about matrices and determinants, they might be finding it surprising. But let me tell you that these are technical things that we have to learn, because matrices and determinants would play on a very fundamental role as we go on. Matrices would start appearing as derivatives of vector valued functions, where one vector space is carried to another vector space, in the sense Rn is carried to Rm. So, when you talk about such functions, for example, we have seen the force function, R3 is carried to R3 just in the last lecture. So, when you talk about derivatives of such functions, then you are really going to express such derivatives in terms of matrices. So, what are matrices? Matrices are, see here in this lecture we will be just considering 2 by 2 and 3 by 3 matrices. So, matrices are arrays of numbers which are written down in forms of rows and columns. So, let me just write down a 2 by 2 matrix. So, a 2 by 2 matrix, which I can write as A if you want, is given as follows. Where so this A11 and A12, this vector in R2 consists of the first row, row 1, and then these are all numbers, they could be real number or complex numbers also. In physics, for example, matrices with complex entries called Pauli matrices are used very much. This is row 2, while this is column 1. Hope I am writing the correct spelling, and this is column 2. So, this is called a 2 by 2 matrix because there are 2 rows and 2 columns. Of course, you can say that can there be 1 cross 2 matrix? Of course, there can be 1 cross 2 matrix, that is, for example, this one, if I just take A11 and A12, then I have 1 row and 2 columns. So, such a matrix would be obviously a row vector. So, this is a matrix. You can obviously, if I talk about 3 by 3 matrices, I can, so I have to add 1 more row and 1 more column. So, I will write them down. So, let me write down what is A11. A1 means the entry in the first row and first column. A12 means the entry in the first row but second column. A21 means the entry in the second row but first column. A22 means entry in the second row and second column. So, this Aij, where I and j are varying over 1 are taking the value 1 and 2, this Aij is called the entry in the matrix. In the matrix, and this entry either is a real number or is a complex number. Either is a real number or is a complex number. So, that is what this is a very basic thing. This A11 and A12, this thing, this stuff, many of you possibly would know, is called the diagonal of the matrix. And when you sum the row 2 elements of the diagonal, if you sum them, that is called trace, which is here same as A11 plus A22. Okay. You can say, can we talk about higher dimensional matrices with more rows, more columns? We will, but not now, later on. So, let us get habituated with simpler things first, and then we will talk about much more difficult things. So, I would expect you to know how to write 3 by 2 matrices now, just an extension. Suppose I call this matrix as A tilde, and this is a 3 by 3 matrix. So, first row first entry, first row second entry, now another additional entry, first row third entry. Similarly, second row first entry, second row second entry, and second row third entry, and similarly we can write down for the third row. So, one row has increased and as a result one column is increased. So, such matrices which has same number of rows and columns, these are called square matrices. These are called square matrices. Associated with every square matrix is a number which we call determinant. So, associated say with a 2 by 2 matrix with a 2 cross 2 matrix A, there is a number which we call determinant of A. There is a number det A denoted by det A called the determinant of A. Called the determinant of A. Now, what is this determinant of A? What is this determinant of A? So, let me write down the determinant of A. So, we are going to consider the 2 by 2 matrix, this one. So, if you have forgotten the 2 by 2 matrix, I just write it down. If you want to, if you do not want to go back and check it, I write it down here. Determinant of A is you multiply A11 with A12, then you subtract from it the product of A21 and A22. So, it is like this, multiply this and then subtract this product of this into this. So, it is A11 into A12 minus A21 into A12. This is called the determinant of A. So, determinant of A is a function which acts on the set of all 2 cross 2 matrices and it gives me a number, and this is the way I calculate that number. You can ask, now you can ask why do you calculate such a thing and what is the requirement. Okay, maybe I should try to explain to you why I write down these things. So, let me just try to give you an explanation. Suppose I have an x which satisfies both these equations. And it also satisfies this equation. So, when can an x satisfy both these equations? So, let us see. So, observe that from the first one here I get x equal to A21 by A11, and from here if A11 is not 0, if A11 is 0 I can't say anything and A22 is 0 I can't say. So, assuming that these are not 0, then I will get x equal to A12 by A22. So, suppose you have a scenario like this. So, what is this? I am just writing it arbitrarily. Let me be more precise on this matter. Let me just write it down in a very simple way. Suppose you have 2 equations A1x minus B1 equal to 0, then A2x minus B2 equal to 0. So, from this I will get x, assuming A1 and A2 not equal to 0, I will get B1 by A1, and from here I will get x equal to B2 by A2. Of course, these B1 and B2 could be 0, then x is 0, okay. Otherwise, suppose B1 is also not 0, then what would happen? Then that does mean that B1 by A1 is equal to B2 by A2, which implies A2B1 minus A1 B2. Now, what is this? So, this is equal to 0, but what is this quantity? Suppose that you take a matrix A hat which is made up of this, also you can take it, you can write it like this, A1 B2 minus A2 B1 equal to 0, just changing the signs. Sure. Let's take it to the other side. So, I can write this as A1 B2, if A hat is a matrix is this A1 B2 and A2 B1. If I have a 2 by 2 matrix like this, then this is nothing but the determinant of A. So, what it says that if there is an x which satisfies these 2 equations when A1 and A2 is not equal to 0 and says assume that B1 and B2 are not equal to 0, then there is an x which will satisfy both these equations simultaneously, when an x will satisfy both these equations simultaneously only if the determinant of this matrix is 0. So, this is sometimes also called an eliminant of this simultaneous equation. So, So, there is there's some link between equation solving and the determinants. We will come to there will be some more things about determinants. You will talk about Cramer's rule in the exercises, and okay, you know how to solve a system of 3 linear equations, and hence we would need the use of determinants. We will talk about it later on. So, now how do I write the determinant of a 3 by 3 matrix? When I have a 3 by 3 matrix, how do I write down the determinant? For example, this one. So, how do I write down the determinant of A? See, 2 by 2 matrix is a building block. So, if you determine the 2 by 2 matrix, when you determinant of a 2 by 2 matrix, then you can also write down the determinant of a 3 by 3 matrix. So, I will start in this way. So, A11, so what do? We take the element in the first row and first column. So, basically then we take off everything that there is in the first row and first column. So, what is remaining is this part. So, we write this in determinant of the matrix A22, A23, A32, A33. Minus, so when I come to A12, what I do is I take off the first row and the second column, but I will put a minus sign. That is the definition of the determinant. I am not getting into detail, but please accept this as a definition. So, when I am in 3 dimension, I am defining the determinant in this way. I am defining the determinant. Assume that this is a definition, right. So, what I am doing is I am trying to use what I know about 2 by 2 matrices or 2 by 2 determinants into this thing. So, it is A12, the signs would be actually plus before these things, minus and plus, and they keep on alternating. You can have a larger matrix also. A12, so into the determinant of the matrix this. So, it is A21, A23, A31 and A33. Then you add A13 into, and you multiply the determinant of, now you take the first row and third column out. So, you are left with this. So, it is A21, A22, A31, A32. Okay. So, this is the definition of the determinant of A tilde, right. So, here why you are using the knowledge of the determinant of a 2 dimensional 2 by 2 vector, a 2 by 2 matrix. Now, there are some facts about determinants that possibly you should know, which is maybe I will just give you some examples of determinant. For example, let me take an interesting matrix. Determinant of all the entries are 1. You can easily calculate that this is 0. This gives us a suspicion that if there are 2 rows which are same 2 by 2 matrix, then they must give me 0 as the determinant value. But that does not mean that if you have all the rows different, you cannot have a 0 value in the determinant. So, for example, determinant of this matrix, which I learned as an undergraduate student, and I was very surprised when my teacher wrote this on the board, because it seems to have some kind of symmetry which I enjoyed 1, 2, 3, 4, 5, 6, 7, 8, 9 is a 3 by 3 matrix and the determinant of this amazingly 0. Of course, there are matrices whose determinant is non-zero, and I need not give you an example for this. For example, determinant of 2, 1, 1, 0, this determinant is 2, so and so forth, right. I am not getting into the larger details of it, but there are some properties about determinants which we should know is the following. Suppose you exchange, suppose you have a 2 by 2 determinant and you exchange the first row with the second row. So, in place of the first row you put the second row, in place of the second row you put the first row. Then what happens to the value of the determinant? Does it remain same or it changes? So, you take A again, which was A11, A12, A21, A22, and then you choose an A bar, for example. So, here what I do, I take the first row and place it in the second row, and second row is taken to the first row. So, I will have A21, A22, A11, A12. Now, let us compute the determinants of this. Now, determinant of A, which you already know, is A11, A22 minus A21, A12. Now, similarly, let me calculate the determinant of A bar. So, determinant of A bar is equal to A21, A12 minus A11, A22, which is same as minus A11, A22 minus A21, A12, and that is nothing but the negative of the determinant of A. So, if you change one row and exchange two rows of the determinant, the sign changes. Suppose I change in this 3 by 3 matrix, I bring it here and take it here, my sign will change. But then if I do again, I will bring this here. So, I took the first row, put it in the third row in the first row. But I now again take the whatever was there in the third row in the change matrix, I take it to the second row and bring the second row there. Again there will be a negative sign and I will get back. So, two changes in a 3 by 3 matrix would give me back the first my determinant value. So, this is a property which you really have to keep in mind. It also works for 3 dimensions, but let us now get into a symbol property. If I take a number alpha and multiply it by with the matrix A11, A12, A21, A22, then my question is alpha of det A, what does it mean? Actually, it simply means that if I am doing so, alpha of det A, so this is nothing but alpha times A11, A22 minus alpha times A21, A12. So, I can write this as alpha time determinant of A alpha, where A alpha is the matrix, say alpha A11, alpha A21, A22, A12. So, you multiplying, basically you may take a matrix, multiply any of the rows or columns by the alpha, scalar multiplication, because these are vectors, ultimately every column or row is a vector, and then you basically it is nothing but alpha times the determinant of that value. So, it does not matter wherever you place it because of this. The same thing happens for 3 dimensions. You really, I would leave you as an exercise to really check for 3 dimensions, which I am not going to get in, because now we are going to tell you something more important. Suppose I do the following operation. I have a 3 by 3 matrix which I am going to do on the board, right. Let me just remove. Now I have this 3 by 3 matrix A tilde, and what I do, I multiply every element of this third row with a number k and add them to the first row, and I construct a new A double tilde new matrix which is A11 plus k A13, A21 plus k A23, that my first row as first column completely gets changed, A31 plus k A33. Now that the second and the third column remains same, A12, A22, A32, A13, A23, A33. Now my question is, I am asking what is determinant of A tilde tilde? The answer is that it is same as the determinant of A. You can play this game. So now let us now construct, I will do some operations on this matrix. So what I will do, I will multiply by a number k this vector. So it will become k13, k23, k33 and add that new vector to this first column, leaving the other 2 columns unchanged. Then I will get a new matrix and I will ask what is the determinant of the new matrix and what is its relation to this old matrix. So I am constructing a matrix like this, A tilde tilde, which is A11 plus k A13, A21 plus k A23, A31 plus k A33. The remaining 2 remain same, A12, A22, A23, A31, A32, A33. Now I ask the questions, what is determinant of A tilde? A tilde tilde rather, sorry. The determinant of A tilde tilde is same as determinant of A tilde, and that is the key. So it does not matter whatever operation you do, you can possibly multiply some k1 into this, k1 into this, k1 into this and add it with the second row and calculate the determinant, you will get the same thing. This has got a lot to do with linear algebra, which you can later on think about. So now we are going to talk about adding matrices. Subtraction is just quite similar to addition, and multiplying matrices. So here I am going to explain to you. First on the board I will talk about multiplying. Now here let me explain to you what is adding of matrices. So when you want to add a matrix, 2 matrix A and B, they must be of the same type. You are adding 2 square matrices, they must have the same order. Have the same order. Means both must be two by 2 or 3 by 3. Any matrix A can be shortened. For example, I have a 3 dimensional matrix, I can write it as Aij and Ij, where I and j take the value 1, 2 and 3. So, these are entries of the matrix, and B can be shortened to Bij. So, both are varying from 1 to 3. So, I is the indicating the row number and j indicating the column number, just as we had done it. So, I am just trying to make you work a little more compactly, making it little more mathematically slightly sophisticated looking. So, you are just doing very simple things. So, A plus B is a new matrix where you are adding your Aij plus B, which has the elements Aij plus Bij, which means if you have A11, so basically what does it mean? So, it is the same Ij. So, if you have A12, then you add, if I is 1 and j is 1, then A11 plus B11. So, you take the corresponding positions. So, if you want to add some another matrix where I have B11 and B12 and B13, so I add with A11, A11 plus B11, A12 plus B12 and so forth. So, this is a short way of demonstrating. Now, I am going to talk about multiplication of matrices, right. You must be asking why you are only talking about 2 by 2 matrices, 3 by 3 matrices, why not 3 by 2 matrices and 2 by 3 matrices. Of course, we are going to talk about 3 by 2 matrices and 2 by 3 matrices, but we will not concentrate on them on this particular lecture, but after 2 lectures we will be really getting in more into details about them, because those kind of matrices would actually play a fundamental role in studying vector valued functions. So, anyway, let us take a 2 by 2 matrix A and B and try to multiply them. I will show you a very simple way. Once you have learnt about the dot product, things are as simple as they can be. So, suppose I have a matrix A 2 by 2. So, if you have only 2 by 2 matrix can be multiplied by with a 2 by 2 matrix. A 2 by 2 matrix cannot be multiplied with a 3 by 3 matrix. Please keep this in mind, and why we have to restrict to this, we will come after 2 classes, 2 classes, right. So, here I have say A11, A12 and A21 and A22, and B, for example, let me take as B11, B12, B21 and B22. Now, how do I compute A multiplied with B? It is all a game of taking inner products. So, let me show you. When we start with A, B, that is you multiply A with B, not B with A. In matrix world, multiplying A with B is not same as multiplying B with A. We will show you by an example, but let me just show this first. So, what we do is the following. We will fill up this place, but let us see how. I will take the first when you start with A, you take the first row of A and take a dot product with the first column of B. So, what is the dot product? A11 into B11, A12 into B21. A11 into B11 plus A12 into B21, A12 into B21. That is the definition. So, now consider the first row and then take the dot product with the second column of this is the first, and so this is a row 1 and this is row 2. So, you take the row 1 and take the dot product with the second column. So, that will give me A11 B12 plus A12 B22. Now you come to the second column of second row of A, and then do the same thing with the two columns of B. So you start with the first column of B, so you will take the dot product, so A21 into B11 and A22 into B21, A21 into B11 plus A22 into B21, and then take the second row and take the second column of B and take the dot product. It is A21 so into B12, first into first, plus second into second, A22 into B22. Look at there is a kind of symmetry. A21 B12, A12 B21, A11 B11, A22 B22. There is a symmetry, and I kind of love this kind of symmetries. And here is A22, here is B22, B21, A12. So this is pretty nice. So it's the same thing you will do for 3 by 3 matrices. Let on homework, just it's out of an assignment, homework for your trial, home try I would say. Multiply 3 by 3 matrices. What are you doing? If you take these rows as vectors, if you write them as R1 vector, R2 vector, and these are C1 vector and C2 vector. So row 1 of A, row 2 of B, row 2 of A, C1 of A, and C2 of first column of A and first column of B. So these are vectors. Then what do I get? I can write AB simply as them simply as R1 A dot product C1 A, R1 A C1 B dot product C2 B. Then you write R2 A, row 2 of A dot product the column C1 of B. So I am writing them as vectors R2 of A dot product C2 of B. That is exactly what matrix multiplication is. Now I will give you an example why A into B is not B into A. So let us take a matrix A which is 1 1 1 1. You know what is this? Determinant is 0. And then take a matrix B which is 1 1 0 0. Is 1 1 0 0. So what is A into B? A into B is take the first column and take the first row of A, first column of B. So 1 into 1 plus 1 into 0, you get 1. And again take the first row and the first column, you will again get 1 here. Here also if you do the same thing, 1 1 1 into 1 0, inner product, again 1 1 into 1 0, get 1 1. But what is B into A? B into A, the game changes. Now I'll start with the rows of the matrix which is on my left side, and I'll use the column of the matrix which is on my right side. So here now I'll start 1 1 inner product with 1 1. So 1 into 1 plus 1 into 1, which is 2. Similarly, keep 1 1 and also take with this 1 into 1 plus 1 into 1, it's 2. Then I'll take the second row of A, B and multiply with, take the inner product with the first column of A, which is 0. Similarly for that is also 0. That is second row of B and second columns of A. So, you see BA and AB are two different matrices. So, product of two matrix is a matrix, but where A into B is not B into A. We are in a world where commutativity which you are so happy with when you are talking about real numbers, AB is equal to BA is invalidated here, it is not valid here. So, with this little interesting feature that mathematics can throw you some interesting tidbits, some interesting facts, we end here, and in the next class we will talk about another very important vector operation, a very different type of multiplication. We have talked about dot product of two vectors which give us a real number. Now we will talk about a cross product of two vectors which will give us a vector. So, with this I end my talk today. Wish you a very good evening and a happy, I would say a happy seeing this video. Thank you.